What if I told you the next global superpower won't be decided by armies? It will be decided by qubits, not bullets, not oil, not even AI as you know it, but machines that calculate in ways the human brain cannot comprehend. Right now, governments and tech giants are racing to build computers that don't just solve problems faster, they solve problems that were never solvable before. And at the center of it all is something incredibly fragile and unbelievably powerful: the qubit. Stay with me, because once you understand this, you'll realize the world is about to change. What makes quantum computing different? To understand quantum computing, you first need to forget everything you know about normal computers, your phone, your laptop, even the most powerful supercomputers. They all run on one simple rule: bits. A bit can be either 0 or 1. That's it. Every image, video, website, bank transfer is just billions of O south and 1 south. Simple, reliable, predictable. For example, breaking advanced encryption, simulating complex molecules, modeling new drugs, predicting climate systems, optimizing massive global supply chains. Classical bits must test possibilities, one by one, step after step after step. That's slow when the possibilities are astronomical. Enter the qubit. Now imagine something different. Not 0, not 1, but both. At the same time. That's a qubit. A qubit uses a property of quantum physics called superposition. Instead of choosing between 0 or 1, it exists in a probability state of both, until measured. That sounds abstract, but here's what it means practically. If you have 2 classical bits, you can represent one of 4 combinations at a time. With 2 qubits, you can represent all 4 combinations simultaneously. Add more qubits, and the power grows exponentially, not linearly, exponentially. Why this is so powerful? This isn't just faster. It's a different category of computation. A 300 qubit quantum computer could represent more possible states than there are atoms in the observable universe. Let that sink in. This is why companies and governments are investing billions, because whoever controls stable qubits controls a new layer of reality. The fragility problem. Here's the twist. Qubits are extremely fragile. They lose their quantum state from the smallest disturbance, heat, vibration, electromagnetic noise. This loss is called decoherence, and it's the biggest challenge in quantum computing. Right now, the race is not just about building more qubits. It's about stabilizing them, because power without stability is useless. Why this matters to you? You might think, okay, that's cool science, but so what? Here's why it matters. Quantum computers could break current encryption systems, revolutionize medicine, redesign materials, transform AI, reshape cybersecurity. The internet as we know it is built on encryption. Quantum computing threatens that foundation. And that's why this isn't just science. It's geopolitics, it's economics, it's power. Section 1, soft close builds suspense. Now you understand why quantum computing is different. But here's the real question. How do you actually build a qubit? Because it's not a chip, like in your phone. It's something far stranger. In the next section, we'll break down the different types of qubits, and why some scientists believe we're closer than ever, while others say are decades away. The different types of qubits and the global technology war. If qubits are the future of power, then the real question becomes, how do you build one? Because a qubit isn't a tiny switch like a classical bit. You can't just shrink a transistor and call it quantum. A qubit must obey the laws of quantum mechanics. And that means it must be built from systems that behave in deeply strange ways. Right now, there isn't just one type of qubit. There are multiple competing technologies, and each one represents a different vision of the future. This isn't just science. This is a technological arms race. Superconducting qubits, the Silicon Valley favorite. Let's start with the most well-known approach, superconducting qubits. These are currently being developed by major tech companies like IBM and Google. These qubits are made using tiny superconducting circuits. When cooled to temperatures near absolute zero, colder than outer space, they exhibit quantum behavior. At these extreme temperatures, electricity flows without resistance, and that allows engineers to create artificial atoms, tiny electrical circuits that behave like quantum systems. Advantages: relatively scalable, compatible with existing semiconductor fabrication, fast gate operations. But there's a problem. They're extremely sensitive to noise. Even tiny disturbances can cause decoherence, which means calculations collapse before finishing. Right now, the challenge isn't just building more superconducting qubits. It's improving their coherence time, how long they can stay stable before collapsing. Trapped ion qubits, the precision approach. Now let's move to something very different. Trapped ion qubits. Instead of circuits, this method uses individual atoms. Charged atoms are suspended in electromagnetic fields, literally floating in space inside a vacuum chamber. Lasers manipulate their quantum states with extreme precision. Companies like IonQ are leading this approach. Advantages: extremely high fidelity, longer coherence times, very precise control, but scalability becomes difficult. You can trap a few ions, but trapping thousands, that becomes engineering chaos. It's like trying to scale a laboratory experiment into a factory. Possible, but complex. Apological qubits, the holy grail. Then there's the most ambitious approach, topological qubits. This is the idea that quantum information can be encoded in exotic states of matter that are naturally resistant to noise. If successful, topological qubits could be far more stable, which would drastically reduce error correction needs. For years, Microsoft has pursued this path, but here's the issue. Topological qubits are incredibly hard to realize experimentally. They rely on theoretical particles that are difficult to confirm in practice. If they work, they could leapfrog other technologies. If they don't, years of research could stall. This is high-risk, high-reward science. Photonic qubits, light as information. Another fascinating approach uses light itself. Photonic qubits encode information in particles of light, instead of fighting decoherence with cooling systems. This method uses photons that naturally travel fast and resist certain types of noise. Advantages: operate at room temperature, easier long-distance communication, useful for quantum networks. The challenge? Photons don't interact easily with each other, and quantum computation requires controlled interaction. Engineering those interactions is incredibly complex. The core problem: error correction. Here's what most people don't realize. A single logical qubit, the kind needed for real-world computation, might require thousands of physical qubits. Why? Because quantum systems are noisy. Errors happen constantly. Quantum error correction doesn't just detect errors, it must correct them without directly measuring the quantum state. And that's one of the hardest engineering problems in modern science. So when you hear Company X built a 1,000 qubit machine, understand this. Not all qubits are equal. Raw qubit count doesn't mean usable power. Quality matters more than quantity. The global technology race. This is where it becomes geopolitical. The United States is investing billions. China is investing billions. Europe is investing billions. Quantum supremacy. The moment a quantum computer solves something no classical computer can, isn't just a scientific milestone. It's a strategic one because quantum machines could break RSA encryption, disrupt financial systems, redefine cybersecurity, accelerate AI model optimization, simulate advanced materials for military tech. This isn't just about faster math, it's about control. Whoever stabilizes qubits at scale could control the next computational revolution. Why stabilization is harder than scaling? Adding qubits is engineering, stabilizing them is physics. Every added qubit increases complexity, more interactions, more noise, more possible errors. It's like trying to build a skyscraper on a vibrating platform. You can stack higher, but instability grows with height. The hidden bottleneck, cryogenics. Many quantum systems require temperatures near absolute zero. That means massive refrigeration systems. Dilution refrigerators the size of closets. Quantum computers aren't sleek laptops. They look like golden chandeliers hanging in vacuum chambers. Until room temperature qubits become practical, infrastructure will remain a major bottleneck. Why experts disagree on timelines? Some researchers say, we're 5 to 10 years away from useful quantum advantage. Others say, we're decades away. Why the disagreement? Because progress isn't linear. Breakthroughs can accelerate timelines dramatically, or challenges can stall them completely. Quantum computing sits at the edge, between theoretical physics and industrial engineering, and that's unpredictable territory. The real question is not just which qubit is best, it's which one can scale reliably. The winner won't be the most elegant, it will be the most stable, the most manufacturable, the most economically viable. So, now you see the battlefield, superconducting circuits, floating ions, exotic topological states, light-based photons, different paths, one destination. But here's what makes this even more interesting. Even if we build stable quantum computers, most algorithms we use today won't run on them. In the next section, we'll break down how quantum algorithms actually work and why they threaten modern encryption. Quantum algorithms and why modern encryption is nervous. Up until now, we've talked about hardware, qubits, cooling systems, stability challenges, but hardware alone doesn't change the world. What changes the world are algorithms. Because a quantum computer isn't powerful just because it's quantum. It's powerful because certain algorithms exploit quantum mechanics in ways classical machines cannot, and some of those algorithms directly threaten the digital foundation of modern civilization. The first shockwave, Shor's algorithm. In 1994, a mathematician named Peter Shor proposed something that changed everything. He developed what is now called Shor's algorithm. On the surface, it sounds simple. It factors large numbers. But here's the problem. Modern encryption systems like RSA rely on the fact that factoring extremely large numbers is practically impossible for classical computers. Take a huge number made from multiplying two very large primes. Multiplying them is easy, but reversing it, finding those original primes, that could take classical supercomputers thousands or even millions of years. RSA security depends on that difficulty. Shor's algorithm changes the equation. On a sufficiently powerful quantum computer, factoring becomes dramatically faster, not slightly faster, exponentially faster. And that's the moment encryption collapses. Why this is bigger than it sounds? Encryption is not just passwords, it's online banking, military communications, government databases, cryptocurrency wallets, secure messaging apps, cloud storage. The internet itself runs on encryption. If large-scale quantum machines become viable, before quantum-safe encryption is fully implemented, there's a vulnerability window, and that window could be dangerous. The second shockwave, Grover's algorithm. Then there's another major algorithm, Loaf Grover introduced what we now call Grover's algorithm. This one doesn't break encryption outright, but it speeds up brute force search problems. Imagine trying to guess a password. Classically, you check possibilities one by one. Grover's algorithm reduces the number of guesses dramatically. Not exponentially like Shor's algorithm, but still significantly faster than classical search, which means symmetric encryption systems must double their key lengths to remain safe in a quantum era. Why quantum algorithms are different? Classical algorithms are deterministic. They follow a clear sequence of steps. Quantum algorithms use superposition, interference, entanglement. They don't just test possibilities. They manipulate probability amplitudes. This is the mind-bending part. Quantum algorithms increase the probability of correct answers, while decreasing the probability of wrong ones. It's not parallel computing, it's probability engineering. The concept of quantum speedup, quantum advantage doesn't apply to everything. You won't use a quantum computer to browse social media. You won't use it to stream movies. Quantum computers excel at specific problem classes: factoring, optimization, simulation of quantum systems, certain machine learning structures. They're specialized tools, but in those domains, the speed up can be massive. The encryption panic. Governments are not waiting. The United States, China, and European nations are actively transitioning toward post-quantum cryptography. The idea is simple: develop encryption methods that even quantum computers cannot efficiently break. Because here's another problem. Data stolen today can be stored and decrypted later. This is called harvest now, decrypt later. Even if quantum machines aren't strong enough yet, they might be in 10 or 20 years, which means sensitive data intercepted today could be exposed in the future. Quantum and AI, the hidden multiplier. Now imagine combining quantum algorithms with artificial intelligence, optimization problems, neural network training, complex simulations. A quantum-enhanced AI could explore solution spaces far beyond classical limits. This isn't science fiction. It's theoretical physics moving toward engineering. The limitation reality check. Here's the honest part. We are not yet at the stage where quantum computers can run Shor's algorithm at the scale needed to break global encryption. Current machines are too noisy, too small, too unstable. But the trajectory matters, because once error correction improves, the leap could be sudden, not gradual. Why this is a strategic weapon in the 20th century, and UCLEAR weapons define power. In the 21st century, information defines power, and quantum computing directly targets information security. Whoever reaches stable, large-scale quantum computation first gains a temporary strategic advantage, not permanent, but significant. The deeper reality. Quantum algorithms reveal something deeper. They show that computation itself is bound by the laws of physics. Classical computing was built on classical physics. Quantum computing is built on quantum physics. And quantum physics allows computation to behave in ways that once seemed impossible. So now you understand the hardware race, the algorithmic threat, the encryption implications. But here's the next big question. Even if quantum computers don't replace classical machines, will they replace entire industries? In the next section, we'll explore how quantum computing could transform medicine, material science, climate modeling, financial markets, and whether the hype matches reality. Real-world applications and the hype versus reality debate. Up to this point, quantum computing sounds unstoppable. It threatens encryption, it bends probability, it challenges classical limits. But here's the real question. Where does it actually matter? Because not every breakthrough becomes practical. Some technologies stay in laboratories for decades. Others quietly reshape civilization. Quantum computing sits between those two possibilities. Let's break it down. Medicine and drug discovery. One of the biggest promises of quantum computing is molecular simulation. Here's the problem. Molecules are quantum systems. Electrons interact in complex probability clouds. Classical computers struggle to simulate large molecules accurately. And when simulation becomes inaccurate, drug discovery becomes slower. More trial and error, more cost, more time. A sufficiently powerful quantum computer could simulate molecular interactions precisely. That means designing new medicines faster, predicting chemical reactions accurately, reducing years of laboratory experimentation. Instead of testing thousands of compounds blindly, scientists could calculate likely outcomes first. This could accelerate treatment for cancer, neurodegenerative diseases, rare genetic conditions. But here's the reality check. We're not there yet. Current quantum systems are too noisy to simulate complex biological molecules at scale. The promise is real. Materials science, designing matter itself. Now imagine designing materials, atom by atom, stronger batteries, room temperature superconductors, ultralight aerospace materials. Materials science depends on understanding how atoms bond and interact. That interaction is governed by quantum mechanics, which means a quantum computer is naturally suited to simulate it. Breakthrough battery chemistry could reshape electric vehicles. New superconducting materials could transform energy grids. Lighter, stronger materials could revolutionize construction and defense. But again, simulation at that complexity requires large, stable, error-corrected quantum systems. We are building toward that. We haven't reached it. Climate modeling, a planetary problem. Climate systems are chaotic. Tiny changes in one variable can cascade into massive effects. Modeling global climate accurately requires enormous computational power. Quantum optimization algorithms could improve. Atmospheric modeling, carbon capture simulations, renewable energy optimization. Better models mean better decisions. But quantum advantage in climate science is still largely theoretical. Classical supercomputers remain dominant here. For now, that means faster portfolio optimization, improved fraud detection, smarter risk prediction. Major financial institutions are already experimenting, but they're cautious because experimental quantum systems must outperform classical algorithms. And that's a high bar. In many cases, classical systems are still faster. For practical workloads, global supply chains are optimization nightmares. Thousands of variables, dynamic conditions, constant disruption. Quantum algorithms could theoretically minimize shipping costs, optimize routing in real time, reduce waste in manufacturing. But here's the catch. Classical optimization methods are already extremely advanced. Quantum must prove a clear advantage to justify cost and infrastructure. That proof is still emerging. The hype problem. Whenever a new technology appears, hype follows. Quantum computing has been called the next internet, the next industrial revolution, the next arms race. But hype can distort timelines. In the early 2010s, many predicted rapid breakthroughs. Progress has been real, but slower than headlines suggested, because quantum engineering is brutally difficult. Every improvement requires breakthroughs in cryogenics, materials engineering, error correction, quantum control. This is not software iteration. This is physics at the edge of possibility. The reality balance. So where does that leave us? Quantum computing is not replacing your laptop. It's not making classical computers obsolete. Instead, it will likely become a specialized accelerator for specific classes of problems. Just like GPUs didn't replace CPUs, they complemented them. Quantum processors may become coprocessors for simulation, optimization, cryptographic analysis, not everyday computing. The economic question: even if quantum computers work, can they be manufactured at scale? Can they be affordable? Can companies justify cost versus benefit? Technology only reshapes society when it becomes accessible, not just possible. The bigger picture: every major computing shift reshapes civilization. Mechanical computing gives industrial expansion. Classical digital computing gives information age. Internet gives global connectivity. AI gives automation revolution. Quantum computing could define the next chapter, but only if engineering catches up to theory. So here's where we stand. The promise is enormous. The progress is real. The limitations are serious. And the timeline remains uncertain. In the final section, we'll zoom out. Beyond qubits, beyond algorithms, we'll ask the biggest question of all. Is quantum computing an inevitable revolution or an overestimated scientific experiment? And what happens to the world if it succeeds? The point of no return when quantum computers change everything. Right now, somewhere in a silent laboratory, a machine colder than outer space is thinking, not like your laptop, not like a supercomputer, but in a way humanity has never seen before. And what it's about to unlock will change everything, because quantum computing is no longer theory. It's already here. Companies like IBM, Google, and Microsoft are building quantum systems. Right now, machines designed to solve problems that classical computers would need millions of years to finish. And when these machines mature, the world will split into two eras, before quantum and after quantum. The end of impossible problems. Right now, there are problems humanity simply cannot solve. Not because we're not smart enough, but because classical computers hit a wall. For example, designing perfect medicines by simulating molecules exactly, optimizing global traffic in real time, creating new materials stronger than steel, but lighter than air, predicting weather with perfect accuracy. These problems involve too many variables, too many possibilities, too much complexity. Classical computers try to calculate every path one by one. Quantum computers explore many paths at once. This changes everything. Instead of brute force, the death of current encryption. Right now, your bank account is protected by encryption. Your passwords, your messages, your identity. Everything depends on math problems. Classical computers cannot easily solve, but quantum computers can. One algorithm alone, called Shor's algorithm, could break modern encryption. Not eventually. Instantly. This means quantum computers could theoretically unlock systems once considered unbreakable. This is why governments and companies are already preparing for a new era called post-quantum cryptography. Because the day a powerful quantum computer reaches full stability, old encryption becomes obsolete overnight, and a new digital world begins. In 2019, Google announced something historic. Their quantum processor solved a problem in 200 seconds. A classical supercomputer would have needed approximately 10,000 years. This moment was called quantum supremacy, not because quantum computers replaced classical computers, but because they proved something undeniable. Quantum computers can outperform classical computers at certain tasks. This was the first crack in the wall. Since then, companies like IonQ and Rigetti Computing have pushed even further. Each year, qubits become more stable. Errors decrease, power increases, and the future moves closer, not slowly, exponentially. When quantum meets artificial intelligence, now imagine combining quantum computing with AI. AI already learns patterns. Quantum computers accelerate optimization. Together, They could create intelligence that learns faster, adapts faster, and evolves faster. Drug discovery could accelerate by decades. Climate solutions could emerge faster. Energy systems could optimize themselves. Entire industries could transform, not gradually, instantly. Problems that once took centuries could be solved in minutes. This is not science fiction. This is engineering in progress. The quantum economy. Quantum computing will not just change science, it will change power. Countries investing in quantum technology today are investing in future dominance, because whoever controls the most powerful quantum computers controls the ability to solve the hardest problems. Financial optimization, military simulations, economic forecasting, material engineering. Quantum computing becomes a strategic advantage, just like nuclear technology, just like artificial intelligence, except more powerful, because it affects everything. But here's the truth nobody talks about. Quantum computing will not replace classical computers. It will exist alongside them. Your phone won't suddenly become quantum. Your laptop won't turn into a quantum machine overnight. Instead, quantum computers will operate in specialized environments, solving problems classical computers cannot, and feeding the results back into the systems you already use. You won't see quantum computing directly, but you will live in a world shaped by its answers. Better medicine, better technology, better systems, built on solutions classical computers could never find. The quiet revolution already started. Right now, quantum computers are primitive, fragile, limited, but so were classical computers once. In 1947, computers filled entire rooms. They were slow, expensive, limited. Most people believed they had no practical future, but exponential growth changed everything. And quantum computing follows the same pattern. Slow at first, then suddenly unstoppable, because exponential growth doesn't feel fast. Until it is. The moment everything changes, there will be a moment, not announced loudly, not celebrated immediately, but a moment when quantum computers cross a threshold, when they become reliable enough, stable enough, powerful enough to solve problems no classical computer ever could. And from that point forward, the world accelerates. New discoveries, new technologies, new possibilities, unlocked. Not because humans became smarter, but because we built machines that explore reality itself differently. Machines that compute using the rules of the universe. The real meaning of quantum computing. Quantum computing is not just about speed, it's about perspective. Classical computers see one path, quantum computers see many. Classical computers calculate reality, quantum computers explore possibility. And possibility is where innovation lives, because every breakthrough begins as something impossible until it isn't. Final message. Right now, quantum computing is at the edge, not fully mature, not fully unleashed, but inevitable. The question is not if quantum computing will change the world. The question is when, because the machines are already being built. The qubits are already stabilizing. The future is already forming, quietly, in cold laboratories, in silent rooms, in machines colder than space itself, and when they're ready, nothing will ever be the same again.